In today's video, we're going to walk through the history of the monitoring systems that EAB Solutions has used over the years. Starting from the simplest systems used to monitor photovoltaic plants, through to more complex systems for monitoring photovoltaics and batteries, both for standard price arbitrage on the spot market and for grid ancillary services, frequency regulation, voltage regulation, and so on. Throughout its history, EAB Solutions has used whatever tools were available at the time to monitor its plants. Mainly, over the course of this presentation, we'll look quickly at how monitoring systems have evolved over time and how EAB has made the most of whatever system was available at each stage. And how, with the 17 years of experience accumulated by the teams behind EAB, we've developed a system that brings together all the capabilities of every separate system that has existed to date, but with a simplicity of use and a far simpler logic, much easier to understand. As we can see here, in the past, whenever photovoltaic installations were built, they were built with PV inverters, often from European brands such as SMA or Fronius, and the monitoring applications of those same manufacturers were always used. In this case, we're looking at platforms from the German manufacturer SMA, platforms that serve to monitor inverter status, faults, production, performance, and so on. For a long time, they let the client and the installer alike know the plant's status, its performance, and how things were running. These are platforms that, over the years, have kept improving in capabilities and in the way they presented information, up to the more sophisticated platforms we use today, such as Huawei's, the Fusion Solar platform, or platforms like 3E Synaptic, which is agnostic to all manufacturers and runs its own calculations to work out the performance of PV plants with batteries, as well as alarm tracking, opening maintenance tickets, and so on. That was it. That was the beginning, when there were standard PV plants, as I say, but a few years ago, batteries started coming into the market. And once batteries were coupled to these systems, managing the whole thing was a little more complex, and there were no tools as simple as the monitoring portals of the solar inverters. So specific tools had to be developed to monitor the battery and the PV side, and to control them if control was needed. So people started developing specific solutions for each project, built by and for that project. Here, what we're looking at on screen is a SCADA made specifically for a project of 2.5 megawatts of PV and 2 megawatt-hours of battery, where the aim was to stabilize PV production, which is considered irregular because when clouds pass or when it rains, production drops suddenly, and the only way to stabilize it is to use a battery to cushion those drops. What you do is charge the battery with the excess energy and discharge it when a cloud passes or when it rains to keep production almost complete. Production much closer to that of a thermal engine or a thermal machine. These SCADA systems were tremendously complex, especially for clients who didn't understand them easily and didn't know how to use them. We installers did know how to use them and how to manage them, but they were not at all simple for the client. They're very interesting systems because they have single-line diagrams, all the detail of all the electronics, every device, every parameter, temperatures, currents, voltages. They're very detailed systems that allow very fine-grained monitoring of the whole plant, and that's very useful for complex plants, but it wasn't much use to the client. Clients always had trouble understanding these platforms, and we always had to explain to the client how they worked, or produce a specific report so they could understand whether their plant was working properly or not. Later on, other slightly simpler platforms were developed. They were still SCADAs, but more visual SCADAs, trying to simplify the information shown to the client. Here, for example, we have the Naldeo SCADA, used for Tesla battery systems and PV installations on industrial buildings, where the aim is to produce electricity on site so the building can consume it, and to use the battery both to store surplus energy and to run arbitrage if needed, taking advantage of spot prices. When they're favorable, that is, low, we charge the battery, and when they're high, we discharge. These SCADA systems were also too complex, even though they use slightly simpler schematics and symbols, simpler single-line diagrams, slightly more user-friendly symbols for the inverters and the batteries. The client still didn't really understand them, and it still wasn't something particularly useful to them. Later, Tesla and other battery manufacturers came along and tried to build their own portals, also with the intention of simplifying things, and their portals we've often used at EAB Solutions, but they haven't brought simplicity either. They're still complex portals for the client, and for years at EAB Solutions, we kept running into the same problem. We didn't have a single platform covering the whole system, the batteries, the battery converters, the PV converters, and all the complex management of the system, in one place simple enough to be understood. And it's along those lines that we had the idea of developing an application where we could show the client things in a much simpler and much more understandable way. An application where the client could quickly understand how their plant works, what it produces, whether it's working well or badly, whether there are alarms, and where we, as the people responsible for the plant itself, wouldn't lose the fine detail, wouldn't lose the precision over the control of the plant, and over the detail of the information that lives in this platform. So the client should know that EAB Solutions always has the portals of the PV inverters and always has access to them. We also have access to the portals of the battery inverters and of the battery itself. But for the client, we've developed this system, our EMS platform, energy management system, designed specifically to simplify all the information exchanged inside the client's system, inside that PV installation where you have the solar production, the output of the PV inverters, the charging and discharging of the battery, electricity prices, the client's own consumption and load, as well as the interaction of all those energies within the client's electrical network. It was a complex problem that we wanted to bring to the client as simply as possible. And that's how our EAB Solutions offering was born, our EMS platform, which we'll now present in more detail. Here, we have the platform running on an example plant. Well, in this case, we have several plants, but this one in particular is a plant the client allows and consents us to show, so that we can show it to other clients and they can see that the system is working, that the platform exists, and so we can explain why we like it and why we think it's the simplest way of showing the client what our EMS does. In this first chart, on this first screen, what you see is very simple. It's an energy flow. It basically shows solar production, here on the right, with the sun symbol. You can see it's producing about 17.7 kilowatts. It's 6 in the evening, the sun is about to set, the day is ending. This is a specific plant of about 200 kilowatts peak of PV and half a megawatt hour of batteries. Right now, these plants are producing 17.7 kilowatts. We see the green dot moving to the center. The energy being produced goes to the center. The center is like the EMS, the brain of the system, and that's where it's decided where that energy goes. In this case, as you can see, 11 kilowatts go to the loads, that is, to the client's consumption, and the surplus is sent to the grid and sold. In other cases, depending on the grid price, or on whether the battery is full or not, that energy would be diverted to the battery, which would be on this side. You can click on any of the icons. Let's click the first one, which takes us straight to a specific chart. Here we have a chart with different colors representing different things. As you can see, there's this dark blue line, which goes down and then rises and stays flat here, climbs to the top, and then comes back down. That's the battery state of charge. It shows whether the battery is discharging, that is, going down. When the state of charge falls, the battery is discharging. When the blue line rises, the battery is charging. When it's flat, the battery is on standby, and so on. In yellow, you have solar production, the typical PV bell curve. In orange, you have what's being sold to the grid, this line that more or less copies the PV curve if we have surplus and we're selling it. Or it drops to zero and turns negative. That is, when we're taking in electricity, whether from the grid. Since orange is grid, it means we're using electricity from the grid or from the battery. The green down here is basically consumption. There are two kinds of consumption: the consumption of the site itself, or the consumption, in inverted commas, of the battery, that is, energy the battery would be taking from the PV or from the grid. On this platform, where there are several curves, let's look for a simpler day to explain it better. Here, for example, what's happening? You have two charts. The lower chart is showing you electricity prices. In red, you have the purchase price of electricity, what it costs to buy electricity on the spot market. And in green, what we'd be paid for selling electricity on the spot market. As you see, the sale price is always lower than the purchase price. We buy dearer than we sell. They buy our energy at a lower price than we pay for it. That's not a problem, because the beauty of these systems is that, as you can see here, this blue curve, the battery was discharged, we said, because it's very low, and suddenly it starts charging. You see the blue ramp start to rise. What's happening is that the battery is charging for one simple reason. Prices are at their lowest point of the day. We take advantage of the grid being very cheap to charge the battery. And once the battery is charged, here you see we're full. We wait. The battery is flat. We wait for the moment of highest price, which is this one here, 18 cents, to discharge the battery. That's the moment when we discharge all the energy we stored. And that way, we're monetizing energy that was charged here at this price, at 3.7 cents, which is what we bought it for in this area, to resell it at 18 cents, which is the line of, and that's how we do price arbitrage. Buying at 3 cents and selling at 18, the difference is 15 cents. So that's how we add earnings to our system. Not only is the site benefiting from the PV production, which feeds the site, and means it needs less energy from the grid, but on top of that, if electricity is very cheap, we're using cheap grid electricity to charge the battery and discharge it when the price is high. And that's where we get an extra, which is what lets our clients not only save on the electricity bill with the PV installation, but save a great deal more on the bill. By running arbitrage on electricity prices, we can go to other days, whichever we want to pick, and see how it behaves. Here we have the same example. What's happening? The battery starts the day relatively low. You can see it here. It discharges here. There's a peak here. You can see perfectly that this peak the battery makes in blue is the battery discharging. Why? Because we have a price peak here. We have 15 cents. They're paying us 15 cents for electricity, so we empty the battery. Here you see the blue line go down. It has emptied part of its energy. Now the battery is almost empty, at 15%. You can see the battery state of charge on this axis here. 15, 30, 45, 60%. So, with the battery as low as possible, we wait for prices to fall. When the price of buying electricity is on the floor, it's very cheap. From 9 in the morning to 4 in the afternoon, we have prices of the order of 2 or 3 cents per kilowatt hour. That's when we take the chance to fully charge the battery. We take all the electricity we can. In this case, as you can see in this yellow curve, the solar production is being stored in the battery. How do you know? You know because the whole yellow curve is exactly the same as the blue curve mirrored, which is this blue area down here. That means the battery is absorbing all the energy the PV produces. Once the PV falls off and we no longer have energy, the battery stops charging because there's no longer that much surplus. We also see the battery has charged and charged and charged until it reached the maximum it's allowed, which in this case is a little less. No, 100%. Here, the axis says 105, we're slightly below. It's 100%. With the battery charged to 100%, what do? Here we do nothing. We have the energy captured in the battery, waiting for an optimal moment to empty it. Like here, electricity prices during these hours of the day, at 2 in the afternoon, at 3, at 4, are very low, so we do nothing. The battery sits still. Suddenly prices start to rise. What does the battery do? It makes a small discharge on this peak. It has captured 9 cents, but since it still has the rest of the day ahead, it does nothing more. Here we have the rest of the prices. Because we load the prices the day before, prices are published the day before, and we have the prices for the following day, so we know exactly what schedule to run. Our EMS knows what schedule to run, and at what time it makes sense to sell the electricity. What's it doing here? Exactly that. The battery keeps waiting, flat, until the moment of highest price. Here we see there are 3 peaks. This step, and this step are the 3 highest. And on those 3 peaks are battery discharges. Here, here, and here. As you can see, the EMS has calculated that it can wait for those 3 peaks, and that over the duration of those 3 peaks, it's able to empty the battery. That's why it waited for those 3 peaks. Because as I say, we load the electricity prices, both purchase and sale, the day before. So we have 24 hours ahead of us with all the hourly electricity prices. We know perfectly well, if today is Monday, exactly what prices there will be tomorrow, Tuesday. So we can organize the day in the EMS to prioritize buying electricity at certain hours and selling electricity at others. What's more, the EMS can perfectly well work out whether it's better, given the electricity prices, and if there's going to be a very strong price at some point in the day, that perhaps it's better to take even the solar electricity, which would normally go to feed our industrial client, and instead of feeding them, charge the battery to make sure we reach the maximum charge, both from the PV and from the grid, and sell it at the moment of highest price. The EMS is constantly calculating what's most profitable, whether the most profitable thing is to feed the industrial client with the PV, or whether there are going to be some really extreme prices. What's most profitable? It's more profitable to sell electricity. If it's more profitable to sell electricity, the client won't be fed and the electricity will be sold. That's the priority. The priority is always that the client gets the best economic return for their kilowatt hours. If their kilowatt hours are more profitable sold to the grid, they'll be sold to the grid instead of consumed at the client's own plant. And that, broadly, is what our EMS does. And here we have it represented in a very simple way for the client. Two simple charts where everything is represented. PV production in yellow, what's being fed into the electricity grid, which is the orange line. The client's own consumption, which is the green shading, and the charging of the battery, which is the blue shading at the bottom of the chart, or the discharging of the battery, which is the blue shading at the top of the chart. As you see, here on this side, you can see that the blue shading, which was battery discharge power, matches the orange line, which is power sent to the electricity grid. Why? Because the battery is discharging to feed the grid, to sell electricity. It's the simplest graphical way of seeing all these elements working in one place. And the same with electricity prices. Down here, you can see perfectly all the hourly prices, how they move every 15 minutes, both purchase and sale. So the client can see whether the decisions their EMS is taking make sense or not, whether the EMS is charging when it's cheap and discharging when it's expensive, or what it's doing. This way, the client, even without being an expert in this kind of system, can easily understand how their system works and whether it's working well. And equally, if too many charts bother them, they can switch curves off by tapping these icons. They can switch off curves one by one. If they don't want to see the PV, they can switch it off. If they don't want to see consumption, they can switch it off. Here, they'd be seeing only battery charge and discharge with its state of charge. If they only wanted to see what the PV is doing, they can switch on just the PV and switch off the rest. So they're seeing what their PV plant is doing and what it produces at any moment. It would be this curve. If what they want to see is what's happening with respect to the grid, that is, are we selling to the grid or are we taking electricity from the grid? They just need to switch on the orange curve directly, and the orange curve tells them what's happening. Right. It's consuming nothing for many hours, feeding the grid in others, and so on. And here, you have that, basically, all this client has done these days is feed the grid. Either feeding directly in hours when there was PV surplus, as here, or feeding at moments when the tariff was very profitable and there was energy in the battery. The client will ask, why haven't we stored this energy here in the battery? Because the battery, in the end, is sized for a case, for maximum return for the client. But maximum return for the client per kilowatt hour of battery isn't always an infinite battery. So there will be moments when there are PV surpluses that don't fit in the battery and have to be sold at whatever price if the client doesn't consume them in their own factory. The beauty is in how we size it. At EAB, we simulate every project with an industry-standard calculation engine fed with the client's real data. We simulate all these surpluses, the exact size of the PV, the exact size of the battery, and which combination of the two is best for the client to get maximum return from their system, taking into account the load of their own site, their hourly load profile for a full year, as well as spot prices or fixed prices, depending on whether we have a client moving to the spot market or a client staying on fixed prices, so that the system always optimizes everything against the client's specific data. They're not generic simulations, they're very specific simulations, made with data specific to each client. And that's why we're confident about the savings we generate for our clients and about the performance of our systems. To work out which system is best for each client, We use simulation tools proven in the sector, fed with measured data from their own installation. The difference between us and other suppliers is that many suppliers just sell the maximum PV capacity because in the end they're a supplier, the typical PV installers. The more PV they sell, the more money they make. So they prefer to give a client an oversized installation because they're going to make more money. What happens? The client isn't going to pay it back as fast. Having built an oversized installation, it will take more years than normal to pay back, which is a loss of money for the client. We don't do that. We're responsible for our system, for our EMS, and our EMS is going to be running at the client's site for years. And during those same years, we're going to be the ones responsible for maintaining that EMS, for supervising that EMS, and for guaranteeing that it delivers the savings we calculated, so that the client, if there's any drift, knows we're there, knows we respond, and that we'll be able to explain why the drift happened. If it has happened, it could be that one year there's less sun and less solar production, or it could be that the client hasn't noticed but has increased their consumption a lot, and that has changed the profile a little, but we'll always be there alongside the client to be able to explain it. Coming back to our system, to our EMS, I was saying it's a system we've tried to make as simple as possible. You can see up here that we show solar production in 3 very simple figures. Today's, which is 1 megawatt hour. This month's, 5.78 megawatt hours. And this year's, 137.9 megawatt hours. We have a weather tab so the client knows whether their installation is producing a little or a lot given the weather. Bear in mind the client may not be at the site. They could be on holiday 2,000 kilometers away. Do they want to know whether their installation is performing well? They need to know if they see the installation is 1,000 kilowatts and it's only producing 10. They ask themselves, why am I only producing 10? If they look at this weather tab, they can see it's raining, that it's a cloudy day, and the weather is bad. And understand perfectly why their installation isn't performing. That lets them see at a glance whether the day is good and production is bad. Something's wrong. If the day is bad and production is exceptionally bad, something's wrong. That's why we have this weather indicator here, so the client understands quickly. Something very easy to grasp. If the weather is very good and there's plenty of sun, there has to be plenty of PV production, so PV production should be high. Unless, as in this case, it's almost 7 in the evening and we're about to get dark. And the third tab is a very easy tab to understand, where we again put 3 fields, which is what was saved yesterday. In this case, we were talking about 3 fields. We were talking about a small installation, as I said, 200 kilowatts peak of PV and half a megawatt hour of battery. Well, yesterday, on self-sufficiency, the client saved €60 in a single day. But, as you can see, the total is 122, almost double. A client reading that asks how that can be. Self-sufficiency is what the PV alone contributed, what energy the PV brought to my site and saved me from the grid. I didn't have to take those kilowatt hours from the grid. I took them from the PV. And that came to €60. But the 122 tells us something else happened at the plant. What happened, basically, is that my battery captured cheap energy at a cheap price from the grid. It charged, and when the price was very high, it fed it back. So automatically, what happened? I ran arbitrage and I earned €60 more. I doubled the client's gain using battery arbitrage. As you can see, this isn't an exception, it's the norm. This is 1 day. But if we look at the month, so far this month, 7 days in, the client has saved €300 on self-sufficiency and has doubled that figure with battery arbitrage. And over the year, they're at €6,687 of self-sufficiency, and more than double in total, €15,572 of savings, thanks to arbitrage. That's why an EMS that manages the system well, that manages the client's loads well, that manages spot prices well, is able to extract far more return than a plain PV installation. People often build PV-only installations because nobody offers them a battery with an EMS that's intelligent enough. We developed this EMS on the 17 years of experience of our teams, precisely to answer that market demand. A market that needed it, that had heard about batteries, where there's interest in batteries, but in the end, a PV installation at a client's site with batteries simply bolted on, and a dumb EMS doesn't produce these kinds of results. It produces mediocre results, because the EMS in those cases only charges from the solar surplus. and the solar surplus usually isn't much, so there's no substantial extra return. The substantial extra return comes from arbitrage done well, and that's where we, with our EAB system, tend to shine. We've been talking about cases where we feed electricity into the grid, cases where we're allowed to, but it's the same principle. What we'll do is charge the battery, either with solar electricity or with grid energy when the price is low, and discharge it against the site's own consumption. If we're not allowed to export to the grid, what we do is supply the site, avoiding any draw from the grid during the expensive hours, which is exactly the same principle. We charge the battery with cheap electricity, and we stop the site from consuming expensive electricity during the expensive hours by feeding it from the battery instead. Another lever we can use, and a very important one in Poland, is improving the opłata-mokowa profile, the Polish capacity fee. Essentially, it means shifting energy out of the peak window, which in Poland runs from 7 in the morning to 10 at night on working days, and moving it into the night hours, so that we cut consumption inside that window and increase it overnight. What does that let us do? It lets us change which days are classified as K1, K2, K3 and K4, substantially reducing the penalty our client pays. It's one of the most important levers in Poland, and it's a lever you can really only activate with a battery. With PV alone you sometimes can, and it improves things quite a bit, but the big change comes with a battery, because that's what lets you move energy from one time band to another. As I say, you take consumption out of the window that runs from 7 in the morning to 10 at night and move it to the night hours. Same as with the battery. Basically, with PV producing in the middle hours of the day, you're already reducing the client's grid consumption, because the client will consume part of that production. And on top of that, if there's PV surplus or a cheap tariff, you'll be able to charge the battery to erase their consumption inside this window, especially in this zone between 8 and 10 at night, which tends to be the most expensive and is still inside the opłata-mokowa window. That way, you reduce their consumption inside the window from 7 in the morning to 10 at night and move part of it to the night hours, making the K1 days go up and the K4 days, which are the most penalizing for the client, go down. That's a lever we use a lot on projects in Poland, and it's very interesting for our clients. There are clients with very intensive consumption inside the peak window between 7 in the morning and 10 at night, and then very low consumption overnight. In those cases, you'd need very large batteries to shift the energy, and it wouldn't be worthwhile. But for the rest of the clients, who have more or less similar consumption between day and night, leaning slightly towards more in the morning and a little less at night, those clients are heavily penalized because they consume more by day than by night, and that is penalized in Poland. With the battery and the PV, we can reduce their daytime consumption, making them consume more at night than during the day. And improving, as I say, those opłata-mokowa penalties. Coming back to the presentation, as I say, we've tried to make it very simple. You can click on the inverters to see the inverter curve, how they're producing by day, by week, or by month. Or even by year, no problem, to see the trends of one inverter, of the other inverter, inverter by inverter, whether they had an alarm, whether they didn't, if we wanted to see the data in real time. Here you see real-time data is shown. It lets us know the inverter is alive, that it's giving voltage, current and power values that are correct, that there's no alarm and that its temperature is right. We've tried to bring the client here the minimum data that carries relevant information. There's a lot more data that we as installers and system managers have, but that isn't relevant to the client, and so we don't bring it here, to avoid making this platform too complex and cumbersome. We also have access to the data logger itself, which likewise gives us a set of summarized data. Again, we've tried to keep it to the fewest and most relevant. Currents on the 3 phases, voltages on the 3 phases, exported energy, reactive energy, which is relevant for many of our clients, active energy, exported reactive energy, exported active energy, and so on. Parameters that are very useful, as well as instantaneous power at any moment, and instantaneous reactive power, and then parameters of the batteries themselves. Whether the battery is charging or not, whether it's at 100%, whether it's empty. For one battery and the other. Batteries have a huge number of parameters, from the BMS itself, the battery management system. But again, that's too much information, not very useful for an end client. In the end, they need to know whether the battery is working, a bit like on their phone. Is my battery at 20% or 80%? And each day it does roughly 1 cycle or 2 cycles to see that it's being used properly. All the rest of the battery parameters don't interest a client. They're not relevant. If the client asks for them, they can be given, but they tend to be parameters that are more of a nuisance than anything else. And that's why we wanted this platform to be as light as possible. As I say, this platform is flexible and allows more things to be added, not just the battery, as we've just said, but if the client has specific consumption they want to monitor, such as cooling or heating systems in their industrial building, it can be connected to current and voltage meters on those particular loads or specific machines the client wants to monitor independently. They can be connected, and you can see their data here in real time in this lower section. And the same applies to clients who want to install charging points for a fleet of electric vehicles. If the client needs it, they can have as many charging points as they need. And on this platform, all the charging points can be monitored, how they are, prioritizing charging of some points over others, limiting charging according to the electricity price. You can perfectly well set the charging points to charge only when there's PV surplus, or when the electricity tariff is very low and very cheap, so they charge heavily at those times. And if the tariff is very high, the charging points automatically either stop charging or drop their charging power a lot, so as not to create too high a consumption. We have total control over the energy management of the vehicle charging points, and the client can program those charging points exactly as they need, according to how they're going to use their fleet, what time they need the vehicles, how many kilometers they'll do each day, how many each week, and the electricity prices at any moment. It's the best way to use an EMS like this to make sure that all the energy the fleet uses has been either produced on site by the PV, or from PV surplus, or taken from the grid at the best possible moments because the price was cheap. As long as that coincides with the moment the client needs the charge. It often happens that clients don't know when they need the fleet. What happens then? Our system, our EMS, works permanently, 24 hours a day, 7 days a week, 365 days a year, learning our clients' operating patterns. It learns how the site's consumption behaves. It learns what it consumes each day of the week, each hour of the week, throughout every day of the year. And every month the system runs, it gets smarter. It gets a clearer picture of the client's consumption pattern. The more years the system runs, the more accurate it becomes, because it's constantly learning, with artificial intelligence, how the client operates and what their consumption pattern is. And the same goes for electricity prices, so it can anticipate and forecast what's going to happen the next day with ever greater accuracy, and the system becomes more efficient and more reliable over time. The same goes for the charging points. If the client doesn't know what their consumption pattern is, it's very simple. You let the system run, and the EMS will learn when the vehicles are plugged in, when they're unplugged, how much they've charged, when the vehicles come back, what state of charge they come back with, whether they've discharged a lot or a little, and how much they need to charge again so as not to run out. The system is constantly learning and knows exactly how many kilowatt hours the charging points need each hour of the day for the fleet to work. And that's what the EMS does. Learn all of that in order to optimize it, cross it with grid prices, and make sure the client pays as little as possible for the electricity used at their charging points, as well as for their site's own consumption. Coming back to our platform, as I was saying, there are a lot of charts here where you can see summaries in different ways, whether stacked bars, both of what's been fed to the grid, to the site, or to the battery, or what's been consumed directly from the PV in green or from the battery, so you can see that part of the energy consumed came from the battery. That is, part of the PV surplus went to the battery, and from the battery went to consumption, or to the grid. As we said, this can be seen daily, monthly, weekly. You can go into as much detail as the client needs or wants. Here, we also have data that interests many clients, especially those with environmental commitments, production and avoided tons of CO2, which can perfectly well be pulled out of the platform if the client needs it for their studies and their annual reports on the environment, on on-site energy production, and on clean energy production. All of this can be adapted to the client's reporting so they have it to hand. Here, As we've shown, you can equally put on a weekly view all the charts that were shown before daily charts of the behavior. Before, we were looking at the charts at power level. We had power charts at 15 minutes, which are these we see on screen. If we want finer detail, our EMS always records everything at 1 minute. It records at 1 minute, even though it monitors at 1 second. And we can go down to 1 minute, which is how the data is recorded in order to do diagnostics and to know roughly what the behavior has been, both in power and in energy. You just change it easily up here, how it's recorded. Here we have the buttons from one to the other, so you can see the data in minute values. If the client doesn't want that level of detail, you can switch to 15 minutes or even to 1 hour. As I say, both in energy and in power. Here on the right, we have summarized data, both of what's happening with the grid, the energy we've fed in, the energy we've consumed in red, and the PV energy as well. Here is availability. The PV inverter is running 100% of the time. It's a very simple way for the client, when they see that number at 90%, to ask why it's at 90. What happened? Did something happen? Did the PV inverter stop? Was there an error? Did something happen? This lets you see it perfectly. The energy charged into the battery and discharged from it. Consumption, total production, and total consumption. These two cover everything produced by the PV plus what the battery has delivered. And this is the whole consumption of the site, plus the consumption of the battery, so it can be seen. And here we have the minimum price for today, 3.7 cents. The maximum price, 36 cents. This is for purchase. The average price, 18. And the spread, which is the difference between the highest and the lowest price of the day, which is 32. You can see it because here prices are very low, 3 cents, and on the sale side 1 cent, and here very high, 36.48. So charging at this point, which is very low, and discharging at this point, is very lucrative and very interesting. And if you look up here, it's exactly what the battery is doing. The battery charged here. Here you see the blue curve rising because the battery power is increasing, and it discharged here. Again. Why? Because the difference between this one and this one already justified discharging. We charged down here and we discharged up here. And then it charged across this whole band. Cheap. This whole band was used to charge. It's the blue line rising to the top until the battery is full, at 95%. And it started to discharge. Here you see all the blue shading, which is the battery discharging to the grid, when prices were very high. The maximum discharge happened up here, right at the price of 36.48 cents, which, as you see, is the highest price. Since we have this data the day before, we're feeding the electricity in because we already knew that at that time there'd be a very lucrative price. And we'd already planned for the battery to reach that hour charged. We charged it. Let's see. And that's basically how it works. As you see, we've reduced most of the tabs to the absolute minimum. So the client sees something very simple, very clear to understand. There are more tabs here, as you can see. The strategy we have active, whether there's a price arbitrage strategy, or peak shaving strategies, or power peak control. Whatever strategy is decided, it can be defined here. It can be switched on or off. So the client sees which strategy we have at any moment, and which one we're using, so that if the client sees different behavior, they can come here and say there's different behavior because somebody changed the strategy. I'm going to ask my supplier, the installer, EAB. That way, the client sees transparently whether we've touched or changed anything. And here, in a very simple icon, they have the alarms. If they see there's a message. In the alarms, they see that 2 days ago, for example, there was a communication error with the batteries. And here they can click and see what time it was, the 5th of August at 2:15, and that the controller couldn't communicate with this device. In this case, it was a one-off error that resolved itself. They're small temporary communication faults. But there, the client can see perfectly whether there's any fault. In 4 icons, we've solved all the complexity that used to sit in this kind of diagram. In the old days, you'd see the SCADAs, all that complexity in these hugely complex SCADA systems that for a client weren't intuitive at all, full of data, of lights, of colors, red, green, orange, text, numbers, currents, voltages, temperatures. something hard to understand, where even any installer or manager of this plant needs half an hour staring at the screen to work out what's going on. Now, we have it represented in an extremely simple way, with our charts and our buttons. One simple central chart showing the energy flow, 4 buttons, you see them here, the home, the charts, the strategy, and the alarms. You click the one you're interested in, and you quickly see what's happening, plus a breakdown of charts, prices below and charts above, where the client understands everything first time. And it's a very simple way of seeing the energy flow, and of making sure clients don't feel lost when they look at the EMS, and that the EMS stops being that magical, mystical box nobody understands. In the end, it isn't complex. The idea is to make your client understand it, so your client can be part of the system you've just installed, so they can discuss it with you, understand how it's working, and even contribute. It's happened to us that clients, reading our platform, have understood how it works and have suggested things. Look, I can see we always have PV surplus at this time of day. Can I shift the consumption of some of my machines to this time to use that surplus? Taking it out of this other period, where the price is high, the client themselves, watching their system run, realizes they can make changes inside their own process to improve their bill and reduce their costs. And that's only achieved when the platform the client uses is simple enough for the client to understand it. And that's the logic of our EAB platform. Questions a client might have, the most common ones, and the ones we're asked most often. What happens if this platform that works so well loses internet access? That's the most common one. Internet access is easy to lose. Sometimes the internet goes down at the site where the client is. Sometimes it's the mobile network and the mast. 4G, 5G, stops working for a few hours. What happens? In that case, there's no problem at all, because as we said, we load the electricity prices the day before, so we already have the schedule planned and calculated for the following day. That is, the day before we've done the calculations for the next day. So the EMS already knows what it's going to do tomorrow. It doesn't matter if today, after downloading the data, it lost its internet connection for hours. It would already have defined its schedule. And when the sun comes up and the PV starts producing, it knows what schedule to run. It knows there'll be cheap prices here. It knows it has to charge at those moments. It knows it has to discharge here, at these moments. And that it has to try to make the PV feed the client's load. Internet or no internet, it will be able to do that. What happens if the internet fails for more than a day? That's where 2 things happen. If the internet fails for more than a day, 2 days or more, what happens is the plant carries on working, but we lose this part down here. We'd lose the ability to know what the electricity prices are. That's not a problem. We lose a fraction of the return we get. We lose the arbitrage lever. We still have the solar energy lever. The sun will keep rising. It will keep producing electricity. Solar energy will keep feeding the client. And by feeding the client keeps not consuming as much energy from the grid, so their PV will keep producing energy that the client consumes. And the surpluses, if there are any, will go to the battery. We have no information on electricity prices because we're disconnected from the internet, but we do have information on the energy flows inside the client's network, so any PV surplus is captured into the battery. The client will simply consume all of their PV output in the site. So the loss is marginal. We've lost the arbitrage information. Of the 2 levers we use, one is on-site energy production consumed by the client. The second is arbitrage or peak reduction. That lever, for example, the client's peak reduction, we'd still be able to do because it simply works by monitoring the client's meter. It doesn't need internet. That would keep working too. The client's peaks would be reduced with or without internet. The internet mainly only affects knowing the electricity prices. Once the internet comes back, we have the electricity price information and everything works perfectly again. And there's no problem at all. Equally, what else can fail? Things do fail. Telling a client it will never fail is a lie. Every client has machines. A site has thousands of electrical and mechanical machines, and they know perfectly well that machines fail. The way to prevent failure is good maintenance. And even with good maintenance, it's hard to stop a machine failing. So you shouldn't tell the client it won't fail. You should tell the client it will fail, and that when it does, we'll do this. And that's what happens. What can happen? It can perfectly well happen that the internet works, but what fails is the battery. If the battery failed, it's very rare, but it can happen that for a day or two the battery fails because of some problem or other. In that case, nothing would happen. The PV keeps producing, the solar energy keeps being supplied to the client. If the battery can't capture that PV surplus, we'd lose two things. The surplus solar energy couldn't be stored, because we have no battery. And arbitrage couldn't be done, because we have no battery, so those two levers would be temporarily disabled. But, as I say, the PV production would keep being consumed, and it wouldn't be fed to the grid, because that's not allowed. In many cases, feeding the grid is prohibited, but that's no problem at all. We don't need the battery. We don't need our EMS either, because we have safeguards. If the EMS fails, the data logger of the PV inverters itself takes care of guaranteeing zero export. In that case, if our EMS failed, the battery failed, and the internet failed, there'd be no problem. The PV inverters would keep producing energy that the client would keep consuming, and if the client doesn't consume it before it goes to the grid, the data logger would prevent it by sending a power limitation set point to the PV inverters. What else can fail? Combinations of elements can fail. What happens if the PV fails? The PV fails, and, for whatever reason, the PV inverters don't work, whether for a few hours or for a few days. No problem. The battery is still operational, and the EMS is still operational. No PV production. It doesn't use it. Does it know the electricity prices? Yes. Does it have an empty battery to work with? Also yes. The arbitrage lever works. The power peak limiting lever works. The battery is able to limit power peaks, so those two levers would keep working. It doesn't matter if the PV isn't working. We'd keep reading electricity prices, charging when it's cheap, discharging when it's expensive, and generating return for our client. And the same with power peaks. If the client is going to draw an excess of X power at a given moment, and that exceeds the contracted power, our battery, which has energy, would cover that excess to stop us drawing more than the contracted power, protecting our client. Which components can fail? In the end, we've mentioned them all. We said the EMS could fail, so yes, let's imagine the EAB EMS fails. We have PV that's working, we have a battery that's switched on and working, but the EMS, which is the conductor of the orchestra, for whatever reason, fails. Which levers are still alive? The PV is still alive. All the solar energy produced will be consumed on site, and if not, it will be power limited or charged into the battery. Why? Because the battery has its own logic inside and has its own EMS. It's simpler. It isn't as sophisticated as EAB's, but it's an EMS intelligent enough to monitor the meter and know there's a PV surplus. Since PV surpluses aren't allowed to be fed into the grid, the battery automatically charges them. It absorbs all that energy. When it sees the client consuming again and the PV can't cover all that consumption, the battery empties to top it up, so the client doesn't have to use electricity from the grid. That is, even if the EAB EMS weren't working, PV and battery would keep working. They work in a slightly less intelligent mode. We lose the arbitrage, but we don't lose all the PV production there is. We don't lose all the surplus energy stored in the battery, and we don't lose the ability to absorb it on site and to respect the zero export required by the DSO. So whichever part fails, we never lose all the levers. To lose every economic lever for the client, there would have to be a total collapse of every system. The PV and its inverters would have to fail, the battery and its inverters would have to fail, and the EMS would have to fail. And the internet. If all four failed, the client would be as they were before the EAB installation was built. That is, with their consumption and the grid consuming in the standard way. But the system is very resilient. It almost never goes completely out of service. And whichever leg fails, the internet, the battery, or the PV alone, it's rare to lose more than 20 or 30% of the economics we were going to generate that day. That's why we consider our EMS to be very resilient, to work very well, and to be very fault-tolerant. Failures are very infrequent. We're talking about well-proven industrial electronics, but they're not impossible. We just want to reassure clients, because 17 years of experience tell us that a failure of any of the parts, the internet, our EMS, the battery, or the PV, never causes a loss greater than 20 or 30% of the savings expected for each day. The worst one that could fail is the one that fails least, which is the PV. In cases where the client has very large PV and consumes a lot of that energy, much of their savings come from the PV. If the PV failed completely, meaning all the inverters, which is highly improbable, then they could lose more than 30, 40 or 50% of the savings. But we're talking about extremely low probabilities. Availability of these systems is around 98%. These aren't systems that fail. They aren't systems that give trouble. We like to explain to the client what happens when any of the legs fails, so they know that none of them causes a total loss of savings. None of them causes a total loss of the economic return our installation generates for the client. So the client can rest easy, because we're always talking about partial losses, often all of them very small, of 10 to 15%. And we have maintenance contracts under which we commit to resolving them in very short times. And on top of that, we hold a stock of parts that lets us replace the parts that fail most often, so the client has availability, as we say, as high as possible, between 98 and 99%. And this is the EMS system developed by EAB Solutions. As we say, an extremely simple system, with the minimum possible information, customizable. If the client wants to see some other custom information, it can be customized. We've tried to keep it as simple, as spare as possible, so the client understands everything and doesn't have too many places to click. You click quickly, the charts appear, you see the charts, you understand the charts. Here on the right is the summary of the data. If you hover over it, you get the floating data for each of the elements and its production. Down here, you have the prices, strategies, and alarms. As simple as possible, in the fewest possible screens and clicks, in whatever language the client needs. In Polish, if Polish is what's needed. For our Polish clients, no problem at all. In whatever language the client prefers. There's no problem in clients having a system they understand perfectly. One they feel comfortable with. And that they don't have to ask anyone for help to explain it. Because it's very easy to understand. Equally, any client who needs help only has to ask, and we'll be there to help. That's been the presentation of our system. And we hope you've enjoyed it.